Welcome to our latest explainer. We're on a global sprint right now. The goal? Reaching net zero emissions by 2050. But to actually pull that off, we are desperately searching for the ultimate clean energy solution. We need something that's as reliable as fossil fuels, but as clean as wind or solar. So, what if I told you the answer might literally be right beneath our feet? Now, this right here is the central dilemma of our modern power grid. Don't get me wrong, solar and wind are incredible. They are the absolute backbone of the energy transition. But they share one fatal flaw, and that is intermittency. You know, the sun goes down, the wind stops blowing. And currently, to compensate for those drops in power, grids have to rely on backup sources. And what are those backups? Well, usually it's natural gas turbines that just pump carbon right back into the atmosphere, or it's massive arrays of lithium-ion batteries, which take a huge amount of resources to manufacture. We absolutely need a better way to keep the lights on constantly. Because intermittent renewables kind of fall short when it comes to providing a constant, unwavering supply. Securing a clean source of what we call baseload power is basically the holy grail of the energy sector. Think about it. Hospitals, data centers, major cities, they don't just go to sleep when the wind dies down. We need a minimum amount of electric power continuously delivered, 24 hours a day, 7 days a week, just to meet our basic everyday human demands. Section 1. Reinventing geothermal power. Meet the Eavor loop. Instead of driving around hunting for unpredictable underground hot springs, engineers are drilling 4,500 meters deep into the Earth's hot rock to create a massive, closed-loop underground radiator. They circulate clean, fresh water through this loop. The water travels all the way down, collects heat from the rock purely through conduction, and then rises back up to the surface. And here's the truly fascinating part. It operates via a natural thermosiphon. Because hot water is lighter than cold water, it naturally rises to the surface on its own, pushing the colder water down. That means this entire circulation happens without needing some massive energy-draining pump. So, how does this stack up to the old way? Well, traditional geothermal energy has always been geographically constrained. You had to rely on hard-to-find local aquifers, and you often had to use risky fracking to increase the rock's permeability. That comes with a high risk of induced earthquakes and requires toxic wastewater disposal. Not great. The Eavor loop literally eliminates all of that. It is a completely isolated closed-loop system. It relies purely on conductive heat transfer. And because you don't need a natural aquifer or fracking at all, it's universally scalable. You can put this thing almost anywhere on Earth. Section 2, the climate impact data. Okay, this number is just staggering. 97%. According to the research, the Eavor loop presents a massive 97% reduction in greenhouse gas emissions when compared to a grid scenario that relies on a solar plant backed up by batteries and natural gas. The life cycle emissions for this system were estimated at just 11.6 kilograms of CO2 equivalent per megawatt hour of energy produced. It fundamentally outperforms solar setups that still rely on fossil fuel safety nets. And we have to consider the carbon payback time. Building any energy infrastructure, drilling rigs, steel pipes, concrete is going to emit carbon. The real question is, how long does that clean energy plant have to run to pay back its initial carbon debt? For the Eavor loop, that payback time is lightning fast. We're talking between 0.3 and 0.5 years. That's less than 6 months. Compare that to a utility-scale solar system with battery and gas backup, which takes up to 7 times longer just to offset its embodied energy. When you zoom out to look at the broader environmental footprint, the Eavor loop only requires a tiny plot of land, just 2.25 hectares, to produce a 6.8 megawatt baseload. Competing solar arrays take up vastly more space, which can really disrupt local ecology. As for water, Eavor's footprint is 12% lower than the solar and battery setup, mostly because manufacturing lithium-ion batteries is extremely water-intensive. And finally, look at air quality. Eavor produces an 88% reduction in harmful air pollutants like sulfur dioxide and nitrogen oxide compared to those battering gas backup systems. Section 3. Balancing the power grid. All right, time for a new acronym, ZELFR. It stands for Zero Emission Load Following Resource. Basically, this is a power source that can cleanly and rapidly adjust its electrical output to perfectly match fluctuating grid demand. Think about it. When solar production drops in the evening, right when everyone gets home and turns on their TVs, a ZELFR steps up. Independent modeling shows that introducing flexible, load-following resources, like the Eavor loop, into a net-zero grid can reduce annual total system costs by up to 21%. That is saving billions of dollars by avoiding the need to overbuild solar and battery storage. But this brings up a super fascinating question. If the Eavor loop is essentially just a continuous flow of water heating up in underground rocks, how on earth can it act like a giant battery to balance out the grid? How does a heat system compete directly with expensive, high-tech lithium-ion batteries? Well, it's called dispatchable power delivery, and here is exactly how they do it. Step 1. During periods of low grid demand, let's say midday when the sun is blazing and solar panels are totally maxed out, the operators actually restrict the flow of water in the Eavor loop. Because the water slows down, heat from the rock begins to build up and store itself in the underground fluid. It's effectively charging the system like a battery. Step 2. When peak demand hits and the sun drops, they open those valves. The system discharges a massive surge of superheated fluid at the surface, allowing it to produce up to 3 times its nominal capacity. So an 8-megawatt system can suddenly surge to 24 megawatts for 8 hours, exactly when the grid needs it most.
Section 4. Geothermal in the real world.
So, is this actually happening? Yes. Let's look at the timeline for the Geretsried project over in Bavaria, Germany. This is the world's first commercial implementation of the Eavor loop. Construction kicked off in October 2022. By July 2023, 2 of Europe's absolute largest drilling rigs, operated by KCA Deutag, started the deep drilling. At the exact same time, they were building the surface power plant. First energy production is scheduled for the fourth quarter of 2024. Once it goes live, this single project will pump out 8.2 megawatts of electrical power. The institutional momentum behind this is huge right now. The European Innovation Fund recently awarded Eavor a $91.6 million grant. That is some profound institutional validation. The Geretsried project alone is going to power roughly 20,000 homes in Germany and avoid 44,000 tons of CO2 equivalents every single year. And it doesn't stop there. Over in the city of Hanover, an Eavor project is being developed to supply 15 to 20% of the city's district heating demand. The ultimate goal? To completely shut down the city's coal-fired power plant by 2030. They are directly replacing fossil fuels with the heat of the earth. So, as we wrap things up here, there's one big question I want you to take away from this explainer today. If the heat right beneath our feet can reliably power the world, act as a massive clean battery, operate with virtually zero emissions, and drastically shrink our land and water footprint, what are we waiting for? The data and the massive real-world investments we're seeing in Germany suggest that closed-loop geothermal might literally be the missing puzzle piece in our global energy transition. It's scalable, and it's happening right now. Thank you so much for joining me for this explainer. Keep asking questions and keep exploring the incredible innovations that are shaping our future.